Hello everyone, I'm Xiaosheng Li from Ant Group. I would like to introduce our work on MMDL-based data augmentation with domain knowledge for time series classification for ECML PKDD 2024. Time series classification is to classify time series data, and currently there has been a lot of work on time series classification. This table shows some of the methods in different categories and the respective methods in each category. Despite we already have a lot of methods for time series classification, most of the current methods only leverage label time series dataset to train the time series classifier and do not use the domain knowledge. But in real-world applications, the domain experts or practitioners often possess knowledge about the characteristics of the time series, which can be used to determine the class label. Here's a real-world example. Part of my job duty in Ant Group includes using time series classifier to handle all kinds of problems. And in this situation, we would like to detect the system anomalies. We use an alarm rule to detect the anomaly. The alarm rule is whether the value of time series drops by a certain percentage in a certain time. From our experience, there is also a situation which we call rise and fall, will trigger the anomaly rule. In this situation, the value will have a rise before it falls. When the value falls, it will trigger the alarm rule. We learned that this situation, in fact, is a normal behavior in our system. So, in fact, it will cause a false alarm. So, we need to figure out such a situation. In practice, we use a time series classifier to do the job. In this case, we have domain knowledge in this process. In this process, we have the knowledge that the class labels are solely determined by the overall shape, and the local details does not matter. If we inject such domain knowledge into a state-of-the-art time series methods, we can boost its classification accuracy from 0.765 to 0.825 in this problem. Here's another example in Ant Group. In the previous case, we used the alarm rule we call percentage rule. But in some situations, like the one we show in this figure, the left part, the time series values oscillate dramatically, making it inappropriate to use the percentage rule. Instead, we should use a value rule. Like if the value drops to a certain value, then it will send the alarm. We would like to distinguish the fast change situation with the slow change situation, which is shown in the right part of the figure. If the value changes slowly, we can use the previous percentage rule to capture the possible anomaly. This rule type determination problem can be solved by the time series classification methods. In this situation, we have the knowledge that the overall shape of the time series do not impact the class labels, and only the texture or the local details can determine the actual class label. And later on, we will show that if we use this domain knowledge into the time series classification process, we can improve its average classification accuracy from 0.858 to 0.903. Our experiments inspire us to generalize or standardize our domain knowledge in many situations in Ant Group into two types. Type 1 indicates that the class labels of the time series are solely determined by the overall shape, and the local details does not affect the class labels. And type 2 is on the opposite side, where only the textual or the local details can decide the class labels. Here is our proposed method. For the situation of type 1, we will extract the essential shapes of the training time series. Then, we will add back them to the training set with the same class labels as their respective original time series. The new augment series can guide the time series classifiers to focus more on the overall shape and just ignore the local details. So essentially, we are injecting our domain knowledge into the classification process. If the situation is type 2, at first we also extract the essential shapes of the training time series. Then we will use the essential shape to receive the residual series, which can be done by just minusing the essential shape from the original time series, as shown in this figure. We add the residual series back to the training set with the same class labels as their respective original time series. Adding the residual series back to the training set can guide the classifier to ignore the shapes and focus more on the local details. So essentially, we are injecting our domain knowledge into the classification process. The remaining problem is how to receive such essential shape. Here, we propose a modified minimal description length based method to extract such shapes. Here's the pseudocode of the process. For each instance in the training set, we will transfer the time series into segments. We combine each of the 3 data points in the time series into a segment and calculate the segment value, which is the mean value of the 3 data points. Then we discretize the segment values and record the length of the segment. In the loop, each time we will merge 2 segments with the minimal merge error. Then we calculate the current model cost and the correction cost of the segment. We sum them up to become the total cost and record the best segment with the minimum cost during the loop. Then we will transfer the segments back to shape series and stop. Finally, we will output all the shapes as the essential shape for the training set. The model cost and correction cost can be calculated using the following 2 equations. The model cost is the information we needed to encode the segment, and the correction cost can measure the difference between the original series and the segment series. From this equation, we learned that essentially the proposed method will encode each element of the difference vector and sum them up to become the correction cost, which is very different from the traditional MDL method. In the traditional MDL method, it uses the Huffman coding length on the difference vector to receive the correction cost. The idea of the proposed method is to encourage the algorithm to find the segment shapes that is very approximate to the original time series. And here's an example. The 2 difference vectors 0, 0, 0, 1, 1, 1, 0, 0, 0, 3, 3, 3 will have the same Huffman coding length, while the first one will have a smaller correction cost according to the previous equation. So it's more preferred in our situation. And this figure shows the essential shape from the previous case. we can see that the shape can capture the overall outline of the time series quite well. And this shows the augment instance for the slow change case. And we can see that the shape can capture the outline of the original time series. And we can just get the ratio series of the local details. To evaluate our method, we conduct experiments on 4 different scenarios. 2 are from our domain of expertise, which has been introduced. They are the false alarm elimination and alarm rule type selection problems. And 2 are from the widely used benchmarks. They are the signal type classification and appliance recognition problems. We compare our proposed method with other time series data augmentation methods. In the comparison, we also include the original MDL version, which uses the Huffman coding length to receive the correction cost. Our domain datasets and source code of MMDL are available online from this link. In the experiment, we will use the data augmentation methods and the comparison to generate new data instance, and then add the new instance back to the training set to form an augment set. We use the Hydro multi-locate time series classifier on the augment set, and then use the classifier to predict the class labels in the testing set. And this is the first case, which we already introduced. In the false alarm elimination problem, we would like to distinguish the time series that has actual drops caused by the actual anomalies from rows belong to the rise and fall situation. We have the domain knowledge that only the shape of the time series can affect the class labels. So the domain knowledge type of the proposed method is set to 1 in this situation. And the rise-fall dataset contains the time series we collected in this scenario. It contains 75 time series of length 60 and their respective class labels. This dataset can be received from the previous link. This table shows the experimental results on the rise-fall dataset. The table shows the testing accuracy and the respective rank for the respective methods under comparison. From the table, we can see that the proposed MMDL method has an accuracy of 0.825, which is better than the version than the method none, which is 0.765. The none method here is indicates the version that we do not apply any data augmentation methods, just using the original training set. We can see that the proposed method indeed can improve the performance of the classification method. Compare MMDL with MDL, we can see that MMDL method has a higher accuracy, which demonstrates our strategy to calculate the correction cost. Overall, MMDL achieved the first rank in this comparison, which shows the effectiveness of the proposed method. And for the second case, we visit the alarm rule type selection. We would like to distinguish between the time series that has fast change and rows have slow change. The percentage rule is fit for the slow change time series, while the value rule is fit for rows with very fast changing. Here, we use a time series classifier to solve the problem. From our domain knowledge, we learned that only the local details of the texture can affect the class label, and the overall shapes does not matter. So here, we set the domain knowledge type of the proposed method to 2. The root type dataset from the link contains the time series instance we collected in this scenario. It contains 239 time series of length 1440 with their respective class labels. And this table shows the experimental resource on this dataset. We can see that MMDL achieved accuracy of 0.903, which is better than the MDL's result 0.893, and better than none, which is 0.858. The result shows the effectiveness of the proposed method. Due to time limit, I would like to skip the details of the remaining 2 cases and just focus on the overall summary. This figure shows a summary of the comparison. It shows the average rank of each method under comparison in the 4 experiments. We can see that MMDL method in fact achieved the best overall performance among all the compared methods. And also, MMDL has better or equal resource on all the test cases than MDL, demonstrating the effectiveness of the proposed method to calculate the correction cost. Finally, in conclusion, here we propose a method to use MMDL process to extract the extensional shape of the time series data. According to the type of domain knowledge, we use either the shape or the ratio of the shapes to augment the training set. In this process, essentially, we are generalizing or standardizing our domain knowledge and inject this domain knowledge into the classification process. Experiments and comparison demonstrate the effectiveness of the proposed method. The datasets and source code are available online from this link. And that's all. Thank you very much for listening.